Well, I will talk about a subject that is of great interest to me, and I presume that it is of great interest to many of you. This idea of using wavefields for imaging and tomography. And we learned quite a bit about that in the past day and a half. There were presentations that introduced various bits of this subject, not least Tariq's presentation of half an hour ago, which was providing quite a bit of detail about waveform inversion. And I personally learned a lot from that presentation, not least the fact that he was trying to fill my shoes when I was gone, which is quite worrisome because he stayed at my house. I don't even want to go there. Okay, so the topic of wavefield tomography is actually quite broad. It is not uncommon to see words like the ones you see here on the slide. Quite extensive jargon: wave equation migration, waveform inversion, wave equation migration, velocity analysis, and so on. And what all these things have in common is the use of waves to produce some information about the subsurface. And it makes sense to think that there are some deep connections between those methods. And I think that we all have that intuition that there must be deep connections between all those methods, although the jargon that is being used has this funny property that it obstructs all those connections. It creates the illusion that we are talking about techniques that are very different from one another. And what I said to do when I was on sabbatical, Tariq, was to try to understand this, first of all, for my own use, because I wanted to get clarity of what those methods do to one another. But, you on camera, Sheila? I knew that. I'll move away. Where was I? I was talking about the fact that I was trying to understand those methods for my own use, but I also wanted to understand them so I can explain to others. And I kept extensive notes on my efforts to dig into the literature. And at some point I decided that I would like to turn those notes into the paper you have in the report now. It's a pretty dense paper. I certainly do not recommend it as bedtime reading. I might give you nightmares. However, what I would like to do in this presentation is to give you an outline of some of the thinking, at least I have when I wrote that paper, and get you at least to follow in the path that I intended for that paper. So I'd like to start by discussing what do we really know in a seismic experiment. And one of the first things we know is the fact that we have a clear geometry, acquisition geometry. We have the known positions of sources and receivers. And I will illustrate all this presentation with the simplest example I could come up with. It looks kind of like this. It's space and it's dark, it's black because we don't know what's in there. But what we know is that we have a source located at the yellow dot, and we have a receiver located at the blue dot. And those are known positions. And we also know that, for example, at the location of the source, we have source function that is injected into the medium, something that looks like this. Now, of course, the fact that we know the source function is questionable. We might argue that, well, how do you really know the source function? So I'll put that important detail aside for the purpose of this presentation. I will assume that we know the source function. You'll see later on that there are ways in which we can ask the question, what is really the source function? This goes into the medium, and we know it, assuming. And out comes this. So we have two pulses that come out of the medium, and the goal of tomography is to figure out what is the medium from information of this sort. Something goes in and something else comes out. Now, another thing that we know, or think we know about this problem is we think that we understand the physics. So we think that we know what is the physical model. We know the wave operator, indicated here by letter L. And this is, for the sake of argument, one of the simplest wave operators one could come up with is the constant density acoustic wave operator, clearly not the one that represents propagation, wave propagation in the Earth by any measure of accuracy, although it is fairly popular operator to use. This also defines the model parameters indicated by letter M here. That's what we are going after. And according to this definition of the wave operator, the model parameters represent slowness squared. So this is not something we know. This is something we assume. We think that we know the physics, and we say, well, let it be this. Other people will make other assumptions, and of course they are, from the physical standpoint, they are superior to this. But for the purpose of what I want to tell you today, this is not too relevant. So I will stay with this definition. And if this is the case, we can do one thing. We can simulate, we can use the wave operator indicated here by letters L and L with superscript T to reconstruct the wave fields indicated by letters U, S, and UR. And we simulate the source wave field, US, by using the wave operator forward in time with a known source function indicated by the S, and we reconstruct the receiver wave field by the adjoint of this operator, LT, with observed data as source function. In this case, we go backward in time. And this is not something out of the ordinary. We do this all the time in migration. We build those wave fields. And they're exactly the same wave fields as we do in migration. I will use throughout this presentation this kind of vector notation because it has advantages for definitions of adjoints if we write it in this fashion. It is not much more fundamental than this. So I hope that the notation doesn't confuse you there. We just have two equations, one going for a solution, a numerical solution for US, and another one going after UR. And those wave fields, again, are like exactly the same ones that we used in migration, depend on lots of parameters. They depend on position in space and time, but they also depend on this other parameter called E, which is an experiment index. This could be, for example, a shot number. For a given shot, we have a certain wave field. For a given plane wave, we have source wave field. For some other kind of encoding, possibly random, we have source wave fields and receiver wave fields. And this E parameter will actually become useful later on, as you will see. Nevertheless, we have those wave fields, and here's an illustration of those wave fields for the very simple model I showed you earlier. I'm showing you this because I will use plots like this throughout this presentation. So hopefully this will not confuse anybody. You see here frames of a movie, starting at the top, smallest time, going to the bottom right, largest time. And there's those small indices there that indicate frame number. And you see here the source wave field, starting at the position of the source, which you see in the top left, and expanding in space according to the local velocity. So you'll see plots of this sort all the time. This is an illustration of the source wave field. Here is an illustration of the receiver wave field, in this case constructed backwards in time. So starting the bottom right, going all the way to the top left. And you might recall that in the receiver wave field, in the observed data, which is the source for this wave field, we have two pulses that we inject into the medium, therefore the two events that you see in this plot. Okay, so we'll approach this problem of imaging inside the Earth from the point of view of an inverse problem. And for that we need to, it is a constrained inverse problem, because those wave fields we keep talking about provide physical constraints. They are not arbitrary quantities. They satisfy a wave equation, an assumed wave equation. And for that we can define the so-called physical constraints indicated here by letters F, subscripts S and R. Fs equals 0, Fr equals 0. These are the physical constraints. And in fact, they simply say that the source wave field is a solution of a wave equation. The receiver wave field is also a solution of the wave equation. Nothing more than that. And with that, we can define this constraint objective function, indicated by letter H. And what we see here, again, we have the physical constraint, Fs and Fr, and we have the two Lagrange multipliers, As and Ar. And this notation doesn't highlight the fact that those Lagrange multipliers are actually big quantities, because they are as big as the source and receiver wave fields. They are not coefficients. They are large quantities applying to every element of Fs and every element of Fr. Coupled with that, we have another element, which is J. This is the objective function, if you want, the unconstrained objective function. And this unconstrained objective function, of course, depends on the things that we have, which are the source and receiver wavefields, on which I will build everything that I will tell you in the next half hour, but also depend on the model parameters. This objective function depends on the model parameters. And this notation you see there at the bottom indicates that we have two components for this objective function. One deals with wavefields, and one deals with the model parameters. And this is fairly standard representation of the data objective function, data misfit objective function, and the model shaping part of the objective function. That's exactly what I'm showing there at the bottom. I'm showing it in this form, and you'll see why. Now, although I strongly believe that this is a huge mistake, I will neglect the second part of this objective function for the remaining of this presentation. So I will assume that Jm doesn't exist. In the paper, you'll see that I talk about it, and I think that that is a huge opportunity and a necessity, if I may say so, for Wavefield tomography. But it clutters discussion, so I prefer not to talk about it for the time being. So we'll stay with the quantity Ju, which indicates that we are operating with the source and receiver wavefields and trying to find a way to characterize how close they are to one another or how they guide us towards a model. And with that, we can construct a gradient like the one you see over here. This has been shown, I think, a couple of times earlier in the meeting. This is nothing but saying that the gradient of the constrained objective function is a cross-correlation, a zero-like cross-correlation of the source and receiver wavefields, the state variables, with the adjoint variables AS and AR, respectively. And we take the zero-like correlation of this quantity, and that gives us the gradient. And it is apparent that what we need to compute a gradient, which is really the topic of my presentation today, is to know two things. We need to know the source and receiver wavefields, which we do, because they are based on solving the wave equation, an assumed wave equation which we choose from source function and observed data. But you also need to solve the adjoint equations, which give us the adjoint state variables, AS and AR. Those are the Lagrange multipliers. And in this case, we reverse the direction of extrapolation. What used to be forward in time is now backward in time, and vice versa. What is key here is the fact that we have a source for the adjoint variables, and the source is indicated by letters GS and GR. What's really useful to know is that GS and GR, the adjoint sources, depend on this quantity I just mentioned, the unconstrained component of the objective function Ju, which depends on the source and receiver wavefields. And what this is telling us is that we will have a different gradient of the objective function when we choose a certain measure of how similar the source and receiver wavefields are relative to one another. In other words, we will try to estimate how closely related the source and receiver wavefields are, and that defines the quantity Ju, and that will constrain or define in itself the adjoint sources, which will define the adjoint variables, which will define the gradient. So the punchline is that if we are going after the gradient of an objective function, what we really want to focus our attention on is the definition of that portion of the objective function, because everything else stays the same. This has been mentioned many times, including here, that we have this adjoint state method foundation, which builds on the existing wavefields, and we have various variations on the implementation that turned out depend on the definition of the objective function, this quantity Ju. In all cases, we are going to use the same wavefields. So that is one of the main messages I would like to leave you with, that all techniques I will describe will all use the same wavefields. They are not different. So far, I did not make any assumption about model parameters. So smooth model parameters versus rough model parameters is not an assumption. We just say, given some model, we simulate the wave fields, and that captures all the information we have in terms of coordinates, in terms of observations, and in terms of assumptions about the wave equation. And all of that is embedded now in the source and receiver wave fields, and that's what we'll work with. Okay. So let's see what options we have. Well, one option we have is to define the objective function with this definition. Ju is defined as a Euclidean distance between the source and receiver wave fields. Now, of course, we know that the source and receiver wave fields have special cases. So the source wave field has a special case, that the source coordinates, the source wave field is the source function. And likewise, the receiver wave field is the observed data as the receiver coordinates. So what we could do is to say, well, let's define the objective function by taking the difference between the source and receiver wave fields. Then we can restrict this difference to either the source coordinates or to the receiver coordinates. And we say that we want to minimize that distance because we know that either at one position or at the other, we want to have the source and receiver wave fields match each other. Now this is, of course, nothing but full waveform inversion in its most basic implementation or most basic definition. Of course, you see that it is based on the existence of those two wave fields. And that will be the pattern that you'll see for all the other definitions that I'll show you later. Okay, so let's see how this works. Here's an example. This is what you saw earlier. The observed data restricted to the receiver coordinates at the top. The source function restricted to a source position at the bottom. I meant the source and receiver wave fields restricted to the source or receiver coordinates. These are, in fact, the data, or the source function. And if we use those, we can construct a difference. And in fact, this is the adjoint source for waveform inversion. Now you notice one here that oftentimes we treat waveform inversion with gloves. We say, well, let's not make the frequency too high. Let's make the frequency very low. And we have other ways of treating waveform inversion with gloves. Here I did not do that. What you notice here is that there's no connection between the pulses that you see over here. We are not within a cycle of one another. And in fact, I pressed hard on this idea because you'll see that this has relevance for what we'll discuss later. So because we have two pulses in the observed data and one pulse in the source function simulated to the receiver coordinates, we have three pulses in the difference, three pulses in the adjoint source. Therefore, there will be three pulses that get pushed into the model when we simulate the receiver wave field, as you'll see soon. So here's the source wave field, again simulated forward in time, starting at the top left, going to the bottom right. Nothing out of the ordinary here. There's a pulse that propagates into the medium. And here's the adjoint wave field, starting at the bottom right, going to the top left. This is propagated backward in time. And you notice that we have three pulses. It's most obvious if you look in the middle panel. Three pulses of different signs. And the reason why we have three pulses is that we have two pulses in the observed data and one pulse in the simulated wave field, which we subtract from the observed data. That's why we have three pulses here. And the correlation between those wave fields will give us the gradient of the objective function. The correlation, the zero-like correlation, effectively means that we take the product of those two wave fields and we accumulate them over time. So time by time frame multiplication of the source wave field in this panel with the adjoint source, adjoint state wave field, the joint wave field seen here, gives us this quantity. And this, again, it doesn't look yet like a gradient because what we ought to do is to integrate. So if we integrate over time, starting at the top, going all the way to the bottom right, that at the bottom is the gradient of the objective function for this particular definition of the objective function with this setup. What we see there are three objects. We see one object in the middle that looks like a fat ray, and then we see two other objects that are elliptical. And at first glance, this might seem like, well, we are now start to understand because there's this object in the middle that looks like fat rays. We've seen that before. That is the sensitivity kernel of waveform inversion. We are used to thinking that way. Although in this case, it has nothing to do with any kind of sensitivity. That low frequency object in the inside, I think you know what I'm talking about. I can't point to it, but you know what I'm talking about. That object is created by the fact that we correlate the simulated source wave field in the background velocity with a back simulated receiver wave field, which contains, through this difference that we took at the receivers, the simulated forward propagating wave field. In other words, we create an event in the back propagating data, which is exactly what we would have by going forward in time from the source function in the background model. And when we extrapolate the wave fields forward in time and backward in time, this event correlates with itself. It doesn't matter what velocity I use there, this event will correlate with itself, because we'll talk about propagation in the same velocity model. That carries no information for velocity model building. The information about the velocity is contained in the other two events, because they will tell us something about pulses that exist in the data and how they interact with the pulse that we simulate from the source. Of course, they look like migration impulse responses, because, as you'll see, they are sort of migration impulse responses. Okay. Now, in case you haven't guessed yet, the model I used to actually simulate the data looks like this. It's, again, very simple. We have a source on the left in yellow, receiver on the right in blue. And we have two paths from the source to the receiver. We have the forward propagation direct path going sideways, and then there's another path going down and coming back up. And in the wave fields that I've extrapolated before, there was no reflector. The model used to extrapolate the source and receiver wave field was constant. What happens if we put this reflector in? Well, here you have it. The source, the observed data remain the same, of course, talking about what we see up here, while the simulated wave field will have two pulses, because now we have the direct path and we have the reflection. And they, of course, they're out of cycle. If we take the difference between those, now their joint source will have 4 pulses. And this will show in the gradient. We'll show that the source wave field looks like this. And again, now in the source wave field, since we have the interface at the bottom, we have 2 pulses here too. We have the direct wave and we have the reflection. We have the direct wave and we have the reflection. And then if this is a source wave field, and the back propagated wave field from the adjoint source will actually have 4 different pulses. And this strange pointer here. Okay, so we have 4 different pulses that look quite complicated. It's pretty hard to make a model that's simpler than this, and yet we have a lot of paths in between. And if we correlate those, again, through integration over time, the gradient is what you see there in the bottom right panel. That is the gradient of this objective function for the setup I just showed you earlier. And like before, the low frequency events do not carry velocity information, because they are simply telling us that the pulse from the source wave field correlates with something else in the receiver wave field, but it's something that we put in the adjoint source. The information is contained by the other events. The other thing we notice here is that some of the things that we saw earlier that seem to look physical, like migration impulse responses that might indicate the position of possibly a reflector, now we have a lot of those. There's a crisscrossing of all kinds of events that interfere with one another. And that is simply because the gradient is just a correlation of the wave fields. If you have multiple propagation paths in one wave field and multiple propagation paths in the receiver wave field, ideally what you'd like to do is to correlate a specific path in one with a specific path in the other. But in reality, that operation, the gradient calculation, will correlate all with all. And you get crosstalk. And this is not surprising, because we've seen this kind of crosstalk, for example, when we do simultaneous sources migration. It's exactly the same kind of crosstalk. Or when we have multiples in observed data. It's the same kind of crosstalk. And that will actually lead me to another take-home message that I would like to leave with you. And that is, first of all, that the fact that we have wave fields that are synchronized with one another may not necessarily carry velocity information, as you see here. In this case, the velocity information is carried by something else. The fat rays do not carry velocity information. Moreover, we have crosstalk between different wave paths, and those cause artifacts. Quite a bit of what you saw in the gradient, that in the bottom left panel, bottom right panel in the previous slide, do not represent anything physical. And that might lead you to think, or to ask the following question, which I asked many times myself. Do multiples help or hurt in waveform inversion? That's a question that I asked different people numerous times. And I will not give you the answer. I will say that for the quiz at the end of this talk. You might want to think about it. I hope that you relax. There is no quiz. For most people, just for Johannes. He's used to that. Okay. So let's move on. If we have all this crosstalk, is there any way we can address it? Well, another way of comparing two wave fields is to say, well, let's correlate them. And that's what you see here. We can define another objective function. Ju is another definition. It's based on the quantity C, which is simply the cross correlation in time between the source and receiver wave fields. The same source and receiver wave fields. We did not change that. Now in this case, we have a different pattern of operation here. We say that the correlation should maximize the zero lag if there is something common in between those two wave fields, and we do not want to turn that into a residual. So we'll apply a penalty function. This is a standard process. That thing indicated in red at the bottom as P of tau. And this penalty function has the only purpose to wipe out everything that is at zero lag and leave the rest. And that will be the residual. Standard process. And with that, we can construct a different gradient. Now, first of all, let's look at an example. Same observations as before. The source wave field restricted at the restricted to the receiver coordinates at the bottom, and then the receiver wave field restricted at receiver coordinates at the top. If we correlate those, we obtain a correlation function, again restricted to the receiver coordinates, that looks like this. What we're seeing here is that we have we have a big pulse located at negative, let's say 0.4, 0.3 seconds. That is a correlation between the path going directly from the source side and the receiver side, and there's a time delay between those. And then there's also, that pulse will also capture the correlation between the paths that go to the reflector. And it turns out that they're not too different in time. They kind of overlap there. And there's a reason for that. I did it on purpose, so I put them roughly on top of one another. The other two pulses are crosstalk. They are not supposed to be there. They are simply the correlation between the path going directly with the path that is reflected in the other wave field, and vice versa. So the crosstalk doesn't disappear in this case. Nevertheless, let's look at the gradient and see what other features we observe here. Now, before I move on, this is not the adjoint source. The adjoint source is the convolution of this quantity that you see here, panelized as a function of tau, and then convolved with the receiver wave field. And that convolution will create, from this function, something that looks a lot like the source wave field restricted to the receiver coordinates. And you know what that means? If we have something that looks like the source wave field at the receiver coordinates, when we backpropagate, this event will correlate everywhere with the source wave field coming directly from the source. And that will create a fat ray. In this case, the fat ray actually carries velocity information. So it is low frequency, but it is a carrier of information for velocity analysis. So let's look at it. Here's the source wave field, nothing different from before. Same idea, we have two different propagation paths. And here's the adjoint wave field coming out of the correlation. And if we correlate the source wave field with the adjoint wave field, we get this. This is the adjoint, this is the gradient in the bottom right here, the gradient of this different objective function. Again, we are using the same wave fields, just change the definition of the objective function. And you see that we have fewer events that interfere with one another, fewer artifacts in the middle. And in this case, as I mentioned earlier, the low frequency signal actually carries velocity information. This is telling us now that we have something correct in this model. And this points out to this difference or distinction between the difference objective function, where the velocity information is contained in something that is highly localized, high resolution, and correlation-based objective functions where the gradient is much smoother, much lower frequency, and that will have consequences. So the message is that by using correlation, we reduce some of the crosstalk because we have fewer events that we allow to interfere with one another. However, the other thing I would like you to take from here is that there is a problem with correlation of the two wavefields. Correlation of the source and receiver wavefields so we can define the objective function. This correlation occurs point by point. We just take a trace from the source wavefield and a trace from the receiver wavefield at the same position and correlate them in time. And it doesn't really matter how the waves move in space at that particular location. In other words, the time correlation does not exploit all the information of the wavefield. The wavefield has a character that involves the directions of propagation, has directivity. Let me illustrate it with a simple example for you. So let's consider these toy wavefields. Wavefield A on the left, wavefield B on the right, same pattern, different frames of a wavefield as a function of time. And here, let's consider another case. Case 2, wavefield A on the left, wavefield B on the right. Now you legitimately expect that when you correlate or you evaluate the mismatch between those wavefields, you get a different answer because they are different pairs. They're not the same. However, if we just do time correlation, as you see over here, we obtain this, case A and case B. And I'm not using the same figure twice. This is, by design, I chose those wavefields to have the same delay, or no delay for that matter, at the middle panel that you saw earlier. So if you look in the middle of the space that where we observe the wavefields moving left and right, there's no difference between those wavefields because we do not take into consideration the fact that the wavefields have directivity or have directionality. But we can do something else. We can use another form of correlation. Let's call this an oriented correlation, for lack of a better name. And what this is still correlation in time, but instead of correlating the wavefields as they are, we shift them relative to one another. And that makes a difference because if wavefields A and B have a certain orientation, if we shift the wavefields in a specific direction, we'll obtain a correlation that is the same regardless of the amount of shift. Okay? This is why this kind of oriented correlation will capture in the output the direction of the wavefield. Of course, this comes at a price. There is more work that we need to do because we have more information we are extracting from the wavefields. But it is simply an extension of what you saw earlier. If we take this shift parameter, this lambda, or space lag, if you might recognize some notation that I'm commonly using. If we make this lambda parameter 0, we get exactly what we saw before. So here's the oriented correlation of the wavefields evaluated at exactly the same location in the middle of that panel. Case A on the left, case B on the right. And in this case, you can clearly see that those pairs of wavefields are not the same. We are dealing with different directions of propagation. The oriented correlation will tell us that information, will capture that information in the output. And therefore, the lesson we get from here is that, number one, we have a way of capturing directionality, and that's useful. But we also have this oriented correlation, which is simply an extension of time correlation. And the word extension will appear later in somewhat different context. So, we have a new measure of, we can define a new objective function, which is now based not on the correlation in time between the source and receiver wavefields, but in the oriented correlation in time between the source and receiver wavefield, as you see indicated by this equation C at the bottom. This is exactly the definition I showed you earlier. In this case, again, we can penalize this correlation to define a residual that goes in the top panel. This is an oriented correlation now, and with that, same inputs, or we can construct a quantity that looks like this. Again, let me explain this. This is a cube. You are seeing here, this is 2D. So we are seeing the vertical shift and the horizontal shift in the inner panel here. So the vertical shift and the horizontal shift, as well as a time lag going along this axis, also this other axis going to the top. And you recognize that the time correlation that we saw earlier is just a trace in the middle of this cube. It's the trace at lambda x equals 0, lambda z equals 0. That is a trace. And you might recall that there we saw 4 events. Here we have 1, 2, 3, 4. Actually, we saw 3 events. There was one that was sort of confusing, was overlapping. 2 events were sort of overlapping at the same time delay. However, if we look in this panel, now we clearly see that these are 2 different events. We can distinguish between the event that is to the left from the event that is to the right. Talking about these events over here. So we can distinguish between these 2 events. And of course, the other 2 are crosstalk that remain crosstalk in this correlation as well. There's no reason not to be crosstalk. Now, what happens here is that with time correlation, we do not have directionality, but we have a much smaller object. With oriented correlation, we have directionality, but we have a much bigger object. And it is legitimate to ask the question, why don't we just go from time correlation, where we have no space lag, to space correlation, where we have no time lag? In other words, what if we shift, or what if we construct an object that looks like this, where we have no time lag, but just the space lag? And this was carefully chosen, this example, to highlight the fact that if we do that, we lose information. I chose this panel to be such that we do not capture all the events in that are part of the wavefield. In fact, we capture only one. And we may capture the others if we make the space lag panel wider, but if we don't, we just lose information. In other words, the space lag dimension is not interchangeable with the time lag dimension. They are complementary to one another. And there's a trade-off between how much effort we put into one versus the other. Okay, so let's see how the gradient looks in this case. Here's the source wavefield, again, the same as you saw before, and this is your joint wavefield. And what you ought to notice here is that the pulse that comes from the receiver is oriented. This pulse goes in a specific direction, doesn't go everywhere. Talking about this pulse over here. This leaves the receiver and it propagates in a specific direction, not everywhere, because the correlation, the oriented correlation, captured the direction in which that pulse arrived from the source, and now it beams it back in the same direction. And therefore the gradient looks even cleaner than we saw before, because now we separate events by the direction of propagation. Now, this is not a specifically illustrative example. There are better ways of looking at this. So let me show you another example, which actually leads to my next topic. Let's assume now that we have the source and receiver in the same position, but instead of measuring the similarity between the source and receiver at the receiver location, we measure that similarity somewhere else. We measure it in this blue box, which happens to be on top of the reflector. And let's assume I know where this blue box is supposed to be. Now, in general, I won't, but let's assume for the sake of argument here that I know. That I know that the source and receiver wavefields ought to correlate there. So here's the source wavefield again. In this case, I'm not putting the reflector, so you see there's only one event. And here's the time correlation back propagating into the medium. And what you notice here is again that this time correlation propagates in all directions, as you see over here. We propagate equally well in all directions, while the oriented correlation will propagate in a specific direction that goes towards either a source or, as you'll see later, towards the receiver. So here's the unoriented or the simple correlation, and here's the oriented correlation. Here we capture directionality in the wavefield, and that leads to cleaner gradients. Here's the gradient obtained with the time correlation, and here's the gradient obtained with this oriented correlation. And some of the interference with these events that appear to the side of the main lobe are not there, because they are corresponding to wavefields that propagate in crossing directions. Same is true for the receiver side, because now we are in the middle. This is the receiver wavefield. Again, in this case, we have 2 pulses propagating backwards in time from bottom right to top left. Here's the time correlation. Again, you see this lack of directionality from the measurement applied on the correlation and the analysis location on the reflector, and this is the a joint Wavefield with directionality. Similar cleanup of the gradient. So the lesson we have from here is that we have ways to clean up some more artifacts by involving the orientation of the Wavefield in the calculation of the gradient. And also, as I discussed earlier, space lags and time lags are not interchangeable. It's not sufficient to say, well, I don't want to compute space lags, I will compute time lags and I get the same thing. The answer is no, you do not get the same things. And in fact, the optimal combination of those might be somewhere in between, where you have some space lags and some time lags, which create a more localized object that characterizes how wavefields are similar to one another at a specific location. Okay, so far, everything we've done so far applies to a specific experiment. So we take one experiment from our survey and we create this correlation or difference or whatever it is, and we create a gradient for that. And then we accumulate the gradients for all experiments. We just sum them up. But we can follow a different strategy. Because what you saw earlier in this last example, I assume that I know where I should do the analysis. And in reality, I don't. And what we ought to do is to create some other object where we know that the analysis holds. And there we invoke the semblance principle. This principle simply says that if we are at a place where waves bounce off in the subsurface, we have, depending on what measures we do, if we apply different measures of similarity between the wavefields, those measures should be consistent with one another at the location only. And that means that if we sum up all these correlation measures, at the location we should get an object that is most localized and most confined. And that's what leads to the next kind of objective function we can define. We are using the same correlation function. In fact, you're seeing there at the bottom, second row from the bottom, the same oriented correlation. But instead of taking this oriented correlation into the objective function, we first sum it up over experiments. So we reduce the experiment axis by one that we take it away by summation. And then what goes into the objective function is the summation of those correlation oriented in this case. Now, conveniently, this quantity is labeled I because it is what we normally call an image. It is what we would call an extended image, but it is really an image. It is a representation of reflectivity, if you want, at the subsurface as a function of position in space, as well as some of those extensions, lambda and tau. And so you notice the point I'm trying to make here is that the image appears naturally. We don't have to work separately for the image. It is just yet another way in which we can measure the similarity between the source and receiver wavefields. And we are talking about the same source and receiver wavefields. We do not change that at all. And if we consider an example, again, slightly similar from what you saw earlier, in this case I will have a source here and a receiver there, again, color-coded source and receiver, and we will look at how this correlation summed over experiment looks at the vertical blue line, or perhaps in this blue box that is conveniently located where the reflector would be positioned if we migrate with the incorrect velocity. We obtain an object that looks like this. Here, vertical, this is space lag, and horizontal. We have so we have vertical space lag and horizontal space lag, as well as time lag. And you've seen these objects before in this meeting and others. What we notice here is that this object is not focused at zero lag, and that indicates that we have incorrect velocity. This is the velocity information that we can use for tomography. And I'll show you a brief illustration of that. Of course, we can ask the question, can we use special cases of what we just discussed? Can we say, well, let's discard the time lag axis? Well, of course, we can, and that means that we have a different correlation. As you see in the second line from the bottom, we have a correlation there that is as a function of space lag and time lag, but then we discard the time lag by the relation that you see at the top. We get a so-called space lag image, or image with, in other terminology, subsurface offset. It's just a special case of the image we saw earlier. And remember, this space lag actually captured directionality. So this directionality is still there. However, we pay a price if we use only space lag and not use time lags, because the space lag need to be large to capture the move out that we would expect of an event at a given location. This is one special case. We can also construct this other special case. We have another objective function where now we discard the space lag and we preserve the time lag in the output. This defines another image which can be panelized like before. There's no distinction there. And in all of these, we involve the same source and receiver wave fields, except that we have this proxy. We have the image which sits in between. And what we take into the objective function, the residual depends on the image as opposed to depending on the correlation function itself. Here are two examples of objects that you might have seen earlier for the exact same setup I showed earlier. Here's a time lag gather. You notice these events with a certain trend which correspond to the local migration velocity. And you see here a space lag gather which has curvature. And of course, since I'm not using split spread acquisition here, you see that this event curves only on one side, not on the other side. Over there, we see just the truncation of the acquisition cable. And with this, we can construct gradients. Again, we're using the exact same procedure. So let's consider this a source wave field, exactly as we saw before. The adjoint wave field for extended images. This, when I say extended, I mean both lambda and tau, both space lag and time lag. This is the adjoint source, which has directionality, as you see indicated over here. So there's some directionality of this wave field going towards the receiver, the source, because this is a source adjoint wave field. On the other hand, the time lag images do not have directionality. They just spread the information in all directions equally well. And if we use space lag only, we have again the directionality. And in this case, I made the space lag large enough that it captures the wave fields themselves. If you don't make the space lag large enough, you simply lose the events. They just do not exist in your gather. And with that, the gradients look very similar to what you're seeing over here. This is for extended images, for time lag images, or for space lag images. And there are lots of details of this, and I don't have time to go into that. But you notice that my point that I would like to leave with you is that you can construct gradients with either one of those measures. They are just alternative methodologies for constructing gradients. And the same happens what you see over here on the receiver side. This is a receiver wave field, and the adjoint wave fields for extended images with directionality, time lag images no directionality, or space lag images with directionality now pointing in the other direction, and therefore the gradients are also oriented appropriately. You see here extended images, time lag images, and space lag images pointing in the same direction. So what's the lesson from this? The images, when you say we have data domain methods and image domain methods, I'm personally ready to discard all that terminology, because in all cases we are operating with the same wave fields. We just have in one case a measure of dissimilarity between the wave fields, an objective function that depends on this proxy quantity, the image. Otherwise, we are operating with the same framework, same wave fields, same underlying theory. And methods that are, say, image domain are not less wave field, not less full wave field than methods that operate in the data domain, because they all work with the same wave fields. That's a lesson that I would like to leave with you, the first lesson. And the objective function, again, what's different in the so-called image domain territory is that the objective function is defined on a combination of all the experiments, as opposed to independent experiments. That's really, if you want, one of the main distinctions between these two classes of techniques labeled as data domain or image domain. The cost, the total cost, is the same, because we are simulating as many wave fields whether we are in the data domain or in the image domain. For every experiment, we need to make two. It's true in the data domain, it's true in the image domain. Except that in one case, we can get a gradient as we go along. For the other case, when we are in the image domain, we need to have all the wave fields so we can build this image on which we can define an objective function, therefore gradient, and then every experiment will have its own gradient. So it's a different pattern, but overall we built as many wavefields as before. So the punchline for everything I want to tell you today is this. We are operating in wavefield tomography with the same wavefields, but we have lots of options. And I show you here at the bottom, just pictorial, that we have 6 options I discussed here. Of course, these are not the only options. The moment when we have more than one option for something, we clearly have more than 2 and more than 6. And in fact, there are people who work with phase. They unwrap the phase of the wavefield and it defines another objective function. They take the wavefield into another domain to define another objective function. They go to the Fourier domain, for example. They go to the Laplace domain. All of those involve manipulations of the same wavefields so we can define an objective function. And after that, the underlying methodology remains absolutely the same. So what it really means is that if we want to compare different implementations of wavefield tomography, we ought to look at the definition of the objective function. And the properties of the objective function will define the behavior and the character of the updates that we get through that particular implementation. And as you will see in Esteban's presentation coming next, those properties are complementary. They are different objective functions have different properties. Some are smoother, produce smoother updates. Others produce rougher updates, higher resolution. These are not irrelevant observations. So I'll stop here, not without acknowledging King Abdulaziz's City of Science and Technology, which is an organization where Tariq used to be affiliated. It's not the one where he is now. They provided quite a bit of funding for my sabbatical stay away from mines. And I would like to also thank you for your attention, and I welcome questions.